So last class we looked at the started looking at the class B output stage. So let's go back before that. What else did we do last class? We did the MOS version of the class A amplifiers, and we did a quick analysis of the distortion. In this particular case, the distortion was due to the body effect, and the threshold voltage changes, therefore your gain will change and you will see a distortion. And we calculated the distortion due to the body effect in terms of the Taylor series, right? Okay. And finally we described something called harmonic distortion, right? You put in a sinusoid, and what you actually get at the output are not only the sinusoid but also harmonics of that sinusoid. Okay? And so we defined second order harmonic distortion HT2 as the amplitude of the 2 omega component over amplitude of the omega component. In this particular case it was some function, okay, of phi f, VDD and so on, and it varied linearly in this particular case with Vi. Similarly, we looked at HD3 and we found that in this particular case it varied as the square of Vi, of the signal input signal amplitude. Okay, so that was as far as the MOS class A amplifier goes. Then we started looking at the class B topology, what is called the push-pull topology. Everybody remembers this? So we figured out the transfer characteristic. So for very small voltages around 0, neither transistor is on, because each transistor requires VBE to turn on, and around this loop you have the requirement that the sum of the two VBEs is 0, right? So because of that you have a dead zone of plus or minus VBE on around the origin. Beyond that, one transistor is off. So for example, when VO is positive, Q1 is on but Q2 is off, because VBE for this increases, VBE for this is already below the VBE on, and it goes on till the point where Q1 saturates. Similarly on the negative side, Q1 is off and Q2 is on, right, until the point where Q2 saturates. Everybody remembers this? Very straightforward stuff. Okay. Now let's draw the waveforms. Let's find out what the maximum amplitude is. We'll find out the output power, efficiency and so on. So let us say this is the input voltage. So this is the output voltage, also a sinusoid. For now we'll neglect the deadband. We'll assume that the input is large enough. Later on we'll quickly draw what happens to the waveforms for different values of Vi, different amplitudes of Vi. For now we'll assume that Vi and Vo are large enough such that the deadbands don't matter. Let's say the peak value is Vo hat. If you draw IC1, during one half of the clock cycle it will conduct, during the other half it's off, and so on. If you draw IC2, exactly the opposite. Correct? And at all times IO hat is VO hat by RL. Right? Those are the peak values of the currents and voltages. This is minus IO hat. Is that okay? In this case, Q1 is on, Q2 is off. Q1 is off. And even though, so because the current is varying as a function of time, you can define an average current, which you can call the DC current. Even though there are cases when the transistor is turned off, you can define an average current, even though you may not be able to define a a well-defined quiescent point which is valid for all time. Why are we interested in I average? Power dissipation, right? Because I average is the current which is the average current flowing from one supply to the positive supply to negative supply. So the power drawn from supply will depend on I average, right? So plus or minus VCC. So the current drawn from the supply is nothing but I average. What is I average? Just call it 1 by T integral 0 to T IC1 of T dt. We just define it with respect to time like this as a sinusoid. Okay? This just happens to be 1 over pi. So in other words, this is psi hat over IO hat over pi. Okay? Is that clear? Should we consider as? Okay, so he has a question. What about IC2? What do you think? So the reason we don't consider that, IC2 will have the, as long as you are in the same limits, IC2 will have the same average as IC1, and your power supply are considering as 2I average times VCC. So one of them conducts during one half cycle from VCC to the output, the other conducts from output to minus VCC. So the average current which is going down, it's the same in both, goes from plus VCC to minus VCC. Right? There are no two averages here. Correct? So this is your power drawn from the supply. Okay? What is the power drawn from the load? Rather, power given to the load. First of all, before we go on to power given from the load, if you look at the power drawn from the supply, what do you see different from the class A? Can you check what it was in class A? Well, it is just 2 VCC times IQ. Okay, in that case. So there's not a lot of, you don't need to look at your notes. But what is the difference between that and here? Huh? Exactly. So one big difference is If your signal amplitude is 0, power dissipated from the supply is 0. And that we already know, right? If your current, then if you don't put in current, your current waveform is just going to be flat. There is no bias current then. Okay. So in other words, the power drawn from the supply is a function of VO hat. So what do you expect this to impact? Efficiency. Right? Fundamentally in the earlier case, you had a constant power spearing down from supply to a positive to negative supply. So you are burning power whether you have an input signal or not. Here, depending on the size of the input signal, you are drawing more current from the supply. So you expect the efficiency to be much better. Right? And the efficiency, do you think efficiency will be a function of VO hat? Actually, let's check. What is PL? We'll write it as half VO squared over RL. Well, this still shows that the efficiency is a function of VO hat. Right? Okay. So the efficiency is nothing but pi by 4 times VO hat over VCC. Correct? So definitely the efficiency is a strong function, linear function of VO hat, which is the peak value of the output voltage. Okay. So what do you expect the maximum efficiency to be? What is it? Pi by 4. Because the maximum swing is almost VCC, right? You can include VCE sat, but it's almost VCC, so it's almost pi by 4. So if you do this, you'll get something like this. We will do the same thing. Okay. So it turns out that the efficiency, the maximum efficiency in this case, is much larger than the class A. In the class A, how much? What is the power efficiency? 25%. Here you have more than 3 times that. Right? So definitely, efficiency, as far as efficiency goes, this is much better, as expected. Okay. Suppose you have to draw the load line. What will it look like? It looks something like this, where VCE or VCC is the quiescent point. When VO is 0, the VCE for each transistor is VCC. And anything beyond this would be like this, would have no IC. What is the other extreme? When you have VCC over RL, right? When VCE is almost VCE sat. Correct? Everybody sees this? The current will be VCC over RL. Is that clear? What is the slope of this line? Minus 1 by RL. So now, of course, the standby current is 0. At the quiescent point, you have no collector current. So the standby current consumption is 0. Is that right? Is that right? No? Yes. Okay. What is the power dissipated in the transistor? It's just IC times VC, collector current times collector voltage. It is going to be a function of time and a function of a number of factors, even including the input signal. So we'll write the VCE as VCC minus ICRL. I out is IC for 1/2 of the cycle, right? So then what we can do is we can find out the point of maximum device consumption, power dissipation, because you have to be worried about this because of device reliability concerns. This will give you PC max. So this gives you V out equals VCC by 2 and IC equals VCC by 2RL. There will be a point somewhere here. Okay. Okay. So now did everybody get that? This is the load line for the class B stage. For this class B emitter follower stage. Okay. Now suppose let's draw the output waveforms. So of course IC1 is going to look like this, something like this. Maximum value is VCC by 2RL, sorry, VCC by RL. It's going to look something like this. Biased at VCC, it's going to go up and down. VCE1, right? Is that right? So if you draw the power dissipated in the device, you'll get something like this. Something like this. You'll get the same 2x frequency, but only for half the cycle. Is that right? In the class A case, it was conducting throughout. Class B case, conducting for half the cycle. And this value is going to be VCC squared by 4RL. This is the peak, PC max. Okay? Okay? Now let's go back to this. So this dead band. So the size of the dead band, this is also called crossover distortion. The dead band is also called crossover distortion. Right? Because right when the input voltage crosses over from negative to positive, you get distortion there because you have no gain. Right? So if you take 3 cases, and let's say the third case, So let us say these are the three cases. What do you expect at the output? So let's say this is Vi. What do you expect for Vo? Let me call this in case 1, what do you expect to see at the output? Huh? So you may have, if at any point it crosses, so you may expect to see something like this. So let us say something like this. Maybe something like this. If during some part of the cycle it actually goes beyond VBE on, you expect to get some gain, but at points where the input is lower than VBE on, you won't get any gain at all. So you'll get something like this. So you get a lot of distortion, definitely. Second case, you may get something like this. This looks okay. You still have some distortion, but as long as the amplitude is much larger than VBE on, you will get distortion, but it will be for a small fraction of the cycle. Okay, I have drawn very badly, but when your input is very large, then you will get clipping at the top and bottom end. So the thing to note is, unlike class A, you have distortion effects for both very small and very large. So if you have a class B stage you are designing or you are trying to evaluate it, you will have to look at the distortion for very small and very large signals. Okay, that part is important. How do you get rid of this crossover distortion? Huh? Insert a diode. Insert a diode where? Here, in the loop somewhere. Okay, will one diode do? You need two diodes. Suppose you insert that two diodes in the loop, right, which have VBE on all the time. What will happen? Instead of having the restriction VBE1 plus VBE2 is 0, you will have VBE1 plus VBE2 is 2 VBE on all the time. Correct? Is that right? And as long as those two VBE ons are constant, you will never get this crossover distortion. So let's see what that will look like. Call this Q1, Q2, Q4. Okay, this is an example of how you would add the two diodes. So now what will the transfer characteristic look like if you had to draw it? Let me move this to the side. What is this going to look like? I assume for very large inputs it won't change much. All you have done is do a small level shift, right? You would think that for large signals it shouldn't change. the characteristic. You are trying to solve only the crossover distortion. Okay. Think about how you would get this. It will be at around minus VBE2. Okay. I want you to go back and analyze and think about how you would come up with this characteristic. Okay. Specifically note where you are applying your VI and see why you are getting your VBE on 2. Right? These 2 points stay the same, no difference. Correct? Yes. You have a current source there. Oh, okay. So you need to have a path for the current. You are right. So quite possibly you may not be directly able to apply VI there. Okay. We'll come to that. We're going to come to that. Because now that we have looked at this, does this look familiar to any of you? So something we have studied before. This is the output stage of 741. Okay. It looked like this. V bias. You had something like this. In the case of this 741. Okay. So you have basically created 2 diode drops. Okay. This is what we studied. I mentioned that we'll come back to this to see, analyze how it works. Right? What is the current, bias current through the output stage? First of all, this is what is called a class AB stage. Okay? A class B stage has crossover distortion. You try to modify that by removing by adding 2 diodes. This is called a class AB stage, because what happens is, for very large signals it is a class B operation. For very small signals, you always have a bias current flowing through these 2 transistors. Okay? So what happens is, during the negative half of the cycle, Q2 will be delivering all the power. Suppose I call this Q1 and Q2. Q2 will be delivering all the power during the negative half. But Q1 will still have a very, very small current, bias current, just to make sure it's on. Similarly, during the positive half of the cycle, Q1 will be delivering all the power. Q2 will have a small bias current. It won't be delivering a lot of power. Okay, it's very negligible. Okay. So this is the 741 output stage. There are actually some more details to the 741 output stage which it's out of the scope, so we'll let it go. In reality, there are some, if you pick up the standard thing, you'll see some resistors here. Okay, you'll see something being tapped off those resistors, and so don't worry about that for now. That is basically for output transistor protection. So to make sure what happens if by mistake somebody shorts the output. What will try to happen? What happens if you try to short the output? If RL is 0, what happens? First of all, PC was a function, the power dissipated on the transistor was a function of RL. Right? Because what will try to happen is, the transistor will try to force the output to be equal to the input, but that is actually shorted to ground. So it will try to pump a lot of current. Right? And eventually the transistor will burn up. Right? To make sure that doesn't happen. So there is a way to protect it, and that's why they add some circuit here, which will turn off the output stage if it draws a lot of current. So this resistor basically acts like a sensor. So if too much current flows, what will happen is this will develop a voltage across it, and you can use that voltage, you can set the resistance value such that if it reaches a certain voltage, in other words, if it reaches a certain current, you turn off. Right? Something like that can be used. Okay? So that is as far as the bipolar stage goes. How about the CMOS? CMOS class AB stages, or class B for that matter. It will look very similar. You can just replace this guy with a Q1 and Q2 with MOSFETs, NMOS and PMOS, and you will get some kind of class B operation. There are some small differences. We'll just take a look at it. What we'll do is we'll draw the class AB stage. Assume that the two sides have no bias difference, so that will be class B operation. Then we'll see what happens in the general sense. Okay, so this is what the CMOS class AB stage looks like. Very similar. You have two diodes in between the two sides. Okay, well, something which looks like two diodes, right? And you have a current source at the top, and of course you have a driver stage. So M6 is what forms the driver stage. Just like in the case of the 741, you had this guy. So similar to that, we have M6. Okay. So first of all, let's quickly analyze this. So you can write KVL around this loop, just as we did in the previous case. Okay. So you have VGS4 plus VSG5 right? This is always valid, the KVL around that loop. So I'll assume that first of all there is no body effect. Okay, so in reality there is going to be body effect, and that is going to change these things, but we'll start off by assuming there is no body effect. Okay, M4 and M5 are biased by some current, so that's why these two sides are using capital letters, so that's constant. VSG4 plus VSG5 is constant. The other side has the signal quantities that will vary with time, but the sum of the two, VGS1 plus VSG2, is always limited to some constant value. Okay, then we'll see what happens first when you go into class B operation. So if you want class B, you are just going to short, the two potentials are equal, the gates of M1 and M2. So VGS1 will be always equal to VGS2, right? So it's very similar to the class B stage for the bipolar case, except that instead of VB on, in this case when VGS1 is greater than VT1, transistor M1 will turn on. Similarly, when VGS of VGS2 is less than VT2, M2 will turn on. You will have a dead band between VT1 and minus VT2. Correct? Is everyone able to see that? Okay. So that part is simple. Now what happens if this is constant, if there's some constant greater than 0? Very easy. So what we'll do is, we'll assume certain things. We'll assume that the VTs of these two are equal. The VTs of these two are equal. W by Ls can be different because that's how you bias the output stage. Right? Output stage has to deliver a lot of power, so it can be much larger. But M4 and M5 can be smaller. Okay? So we'll assume this. Of course, we're also going to assume ID4 is minus ID5, so the two currents are equal in 4 and 5. Now we can rewrite the KVL, the same this equation here, we can rewrite it in terms of the currents and the W over Ls and so on. Right? We'll do that. So this is the left hand side. What do you use here? Do you use ID2 or ID1 or what do you do? Ideally, okay, in reality it should be ID2. What we'll do is we'll assume that we are doing the case when V out equals 0. Therefore ID1 equals ID2 equals minus ID1. Right? If you remember, we analyzed the 741 output stage, found out the bias currents and so on, but we did it at the case when V out equal to 0. The reason is, when V out is not 0, it goes into class B operation. And the two bias currents will no longer be the same. The two currents will no longer be the same, not necessarily the bias currents. Right? Is that clear to everyone? So that's why we'll do the same thing. We'll assume V out is 0. Okay? So now we can replace, because V out is 0, I'll call it capital ID1. You'll get some dependence like this for ID1. So far so good, because it looks like the output bias current is well behaved, because it depends on the W over Ls and it depends on the bias current which is also well controlled of ID4, bias current of M4. right? What is the output positive maximum? Suppose VO is swinging. How high can it swing? What is it? VDD max, VDD minus VD sat of what? M1. Is that right? Huh? VD sat? Exactly. Be VDD minus VD sat VD sat. Let's say VSD of M3 minus VGS1. Right? That is how high you can go for proper operation. Correct? So the reason I am asking you is, don't blindly say, if I ask you for output swing limit, don't blindly say VDD minus VD sat, right? Try to look at all different parts of the circuit which are being affected and then decide. Okay? So this is your positive maximum, right? I mean, of course, the VSC3 is, you can manipulate it because after all a current source, you can bias it close to its saturation voltage. Okay, so what else? Can you do a common source? Yeah, you can. Right. In this case, we have just looked at class A, class AB, class B with emitter followers and source followers. You can bias a common emitter or a common source in similar format. In fact, the original archetype we looked at on the first day when we started off output stages was actually a common source with a current source. The common source amplifier with a current source. If it's biased at VT, it is class B and so on. That's what we decided. Right? Is that right? So what we did was the case with emitter followers. But in reality, any kind of amplifier can be used in different, depending on how you bias it, can be used in these different modes. Okay? We'll just look at a quick case with, there's just an example of a common source amplifier with error amplifiers. So in this case you have a PMOS. Okay. What you are going to do is something like this. Okay. What will the amplifier do? It will drive VO equals to VI. Right? That's what it's going to do. So this is definitely a case of negative feedback through the common source, through the amplifier and then through the common source. Right? Okay, so this is what the amplifiers are going to try to enforce, VO equals VI. Why would you want to do this in a general case? Why not just directly use M1 and M2 and connect input to output? What are the other effects of negative feedback? What else does it affect? So if you have an amplifier like this, what do you want the output impedance to be? If you have a power amplifier like this, you want it to be low, right? If you just directly use the MOSFET, what is the output impedance? It will be the RDS1 parallel RDS2, which will be quite high. Correct? And we know that negative feedback tends to move it towards the more ideal case. Anyways, I want you to analyze the negative feedback in this. You can show that okay. So it will be R01 parallel R02 parallel 1 over GM1 plus GM2 times A. Okay. And of course, in a typical case, you would probably want to make GM1 equal to GM2 if you want very symmetric positive and negative sides. Okay. In this case, the loop gain is actually, yeah, I'm assuming GM1 equal to GM2, so it's 2A GMRL. What do you expect the error in, well, let me just say, I want to call it DC. Error in V0 should look something like 1 over loop gain. I think that's what we have seen before. In this particular case, it also happens to be the same case. If you analyze this, you should get something like this. You should get something like this. The ideal case is 1. Correct? And as A increases, it pushes it towards the limits. Right? Towards the ideal case. What will happen if these amplifiers have offset? It will change the error, definitely. Right? Okay. So let's stop here. So tomorrow's class, so we have 2 classes left, right? So tomorrow's class we'll do the class C amplifier that was given actually as one of the tutorial problems, because the latest homework which was listed has 3 problems. So the first 2 things are very easy, right? The band gap amplifiers, first 2 or 3 are very easy, just extensions of what we have done in class. That should take you